Thanks very much for the introduction. So it's really my pleasure to come here to give a presentation on the unified acceleration framework of both the large language model and also Stable Diffusion. And this will be on the edge. But on the cloud is also similar. So I think people know that machine intelligence or AI is so popular now. And then, but the next generation of AI, people are focusing mostly on the large language model and also the other generative AI like Stable Diffusion, video diffusion, and also the multimodal applications. These are somewhat like dominating and is beginning to explode in the cloud communication cost, cloud computing cost. But there is a problem here, is that people want to ask this question, whether the cloud can actually satisfy the needs. What is the actual user's needs of this kind of models? And are they actually going to be satisfied by the cloud service providers? So actually, the users has very diverse needs. So this is actually a screenshot from the famous it's called the Civitai. So actually, the people are not simply running the original models of the Stable Diffusion. People are running the different checkpoints, different initial models, and also different LoRa modules. So even GitHub or the Hugging Face these days cannot satisfy the people's needs in the Stable Diffusion. Actually, people are more and more using this kind of Civitai or automatic 111, this kind of collections, because they incentivize the people to actually upload their specific checkpoint. And then for the designers, for the actual people who use this kind of models, they need this kind of thing. Instead of a general model, because all the data and even the structure are modified. But the problem is that the cloud service providers, they are mostly only support the fixed models, like the fixed Stable Diffusion XL, like the fixed Llama version 3 or the Mistral. They're using fixed model, and then they are grouping users' requests such that they can make profit. But to be honest, they didn't make profit. Only NVIDIA makes profit. So they cannot satisfy the actual user's needs because every user needs to use different models, and they want to modify those models. And then there are tens of thousands of models that cannot be satisfied from any of the cloud service providers. So if you can see, they only support at the level 10, 20 fixed models. So we're going to a new notion called the user-centric AI deployment. It means that each user wants to deploy whatever the AI model they want and whatever is actually needed in their development. So there is a set of requirements. This is a list from the most important to the least important to my understanding. But I will not say that they're least important, but at least the first one or two is a killing point. If that cannot be satisfied, then that cannot satisfy the user's need, definitely. The rest of the two are somewhat like we can compromise. The first is that whether it is click and run, whether it is plug and play and easy to use. So we shouldn't have an expertise of the hardware platform. And many people even don't need expertise of the model, but they just want to use. The second one is actually the cost. It's better to use the existing software compared with the expensive software. For example, it's better to use the current PCs, the current laptops, even mobile phones, better than the local device, local servers, and then more preferable than the cloud. If we say that the users have expertise, and then they just want to rent A100 or H100 using the Amazon AWS, which costs about $4 per hour, and then they can just upload any model, and then they can configure and in multiple hours and just run it. But what if they want to change the model? And for most of the cases, he or she is not using this hardware. It's just a waste of time. And it costs thousands of dollars per month, which is just not tolerable for the users. So this is the reason that people prefer the local devices. The third is the generality to the different large-scale AI models. Large language models, stable diffusions, video generation, so on and so forth. And the last is the high performance and specifically local processing for the fine-tuning. I will say that the first is actually the killing reasons. But the last is something that we can compromise a little bit. But it's still better that we have the high performance and privacy. Existing work is mostly dependent on the DNN, the so-called compilation. This compilation is that we are from a model, and then we are essentially testing the different configurations on the target device. We can see that there is a large number of so-called compilation methods. And those compilation methods are tests for different memory layout, testing for different parallelism, tiling for each of the layers, and the further connection between layers of a whole neural network. We can see that there is a large number of compilation methods, and then the representative ones including the TensorRT, LLM, which focus mostly on NVIDIA, and the Core ML, which focus on Apple, TVM, and which is, they call it general compilation, but actually requires the users to write the operators themselves. So there are some common shortcomings here. One is that it is very time-consuming. It takes up to weeks or even months to support a new model. This is even for experts. And the second is that it requires special expertise, which is very difficult to use for general users. The general users will be designers for this kind of large language models and Stable Diffusion. They are just marketing people, advertising people, and they're making cartoons. But how can they anticipate them to learn about compiler, about hardware? They just want to change a different model and then just click and run. So this is some killing reasons. And also there are some other shortcomings, but those are secondary. For example, their performance or their optimization is not for the large-scale models like transformers. Or there is a limitation of the operator set, mostly OminiX. And those have something like 2 gigabytes of the constraint, something like this. But let's say this is secondary. The first two is a killing reason for this. We give some data points of how those compilers are actually used. So those are some of the data points. So we see here, the first two is actually the official use of TensorRT. And currently, TensorRT cannot support Llama 2. Why? Because Llama 2 has a slight modification. TensorRT is everything needs to be fixed, and then you can compile it. But it has been fails for over 1 month because of a small modification of Llama 2 structure. But then we cannot compile until now. Second, general TensorRT, if we want to support a small model, not even a large model, it generally takes about 1 week to configure it for an experienced PhD student or an engineer. Generally, people want to avoid this until the model is fixed, and the last step is to use TensorRT. How can we anticipate that this can be done by general users? Because in the whole world, there may be 100 million or more of the users who wants to use Stable Diffusion or large language model, but who wants to use it. But there may be 10,000 people who can use TensorRT. So there is a big gap here. And if we give some other samples, like the Core ML, which is actually for the Apple or for the Mac devices, our work with Snapchat on the Snap Fusion, if we want to implement on an iPhone, it takes several engineers in Snap. And this is done for over 1 month just to deploy it after we train the model. And also our work on video generation on Core ML. And actually, for this work, we have started from last December to now, but the compilation is still fails. It's still not possible. So if we say that, okay, come on, we may be not the experts of Core ML. So maybe some of the experts, and this is actually the supporting top line from actually one of the top researchers in the compilers. And you can see that from his timeline, this is already over 1 year. This is a project start with is last year this time, and then this is now. And we can see that from over 1 year of span, they support about 10, 20 models. So even for the experts, the world-leading experts of compilers, their speed is supporting 1 new model in 1 month. Then the problem is that how to support this. So this is the reason that we see that for the compiler-based models, if we compare on the easy to use or the generality, and then they have really 0 scores. And then the generality to models is maybe okay, and the performance may be okay, but also there is some shortcoming because the traditional compilation or acceleration technique typically will not work for the large language models or not work well. So there is another trend, another direction, and then this is through the so-called Llama CPP. And then this Llama CPP is even, to be honest, is even more useful compared with most of the compilers. So this is a reason that this one has attracted a lot of interest these days. Llama CPP is a very good engineering work. Actually, it is a combination of a PyTorch, but it is using the C-based, C++-based backend, and it only works for the large language model. Because it actually uses C++. So actually it has a good generality to the different platforms, limited, but still okay. It at least can work for the Mac device, for the Intel device, not Qualcomm at this moment, and also work for NVIDIA. Okay. So, but this also has some shortcomings. So we can see that the front end is still difficult to generalize to all types of neural network models. It only works for the large language model, but not Stable Diffusion or this kind of multimodal models. And also is lag or a little bit incompatible with back-end optimizations. So, and also there is no advanced back-end there, so the speed is okay, but it is relatively slow. So there are many of the APIs built based on the Llama CPP, like Ollama, like LLM Studio, and so on and so forth. And we can see that with those APIs, the easy-to-use score is very high. But then we can see that the generality to the models is limited, only large language model, no other models. The performance is okay, but weaker compared with the compilers. The generality to the platform is better than the compilers, which is also okay. Doesn't support any on-device training. So we can see that if we consider the satisfy for the user needs, this one is better compared with the previous methods of the compilers. The compilers is really cannot be used. But Llama CPP is a good solution. Our envision of the operator set and the acceleration framework needs to satisfy everything. We need to be plug and play, easy to use, means that we just click and run. We do not need to use the time-consuming compilation phase. We need to have the generality both to the models and platforms, to all types of large-scale models, small-scale models, and also to all types of platforms. We need to have a high performance. That means that 3 times to 10 times speed up compared with current frameworks. We need to support on-device training, and also we should relieve the constraint on the operator set. So a brief discussion of our technology. So actually, our proprietary runtime technology is going to overcome the limitation of the current tech work. We have the technology to make it plug and play and to make it general. That is an effective decoupling of the front end and the back end. Currently, it is not done well. And also, all our acceleration techniques are instantaneous. Current compilation is essentially trial and error. So they're just going to test different configurations. But we directly arrive at the configurations. Actually, from our past 2-3 years, we have been working on this kind of instantaneous optimizations. But then there is not much need for this. But nowadays, we found that local deployment, and also people are using a diverse aspect of LoRa's and the fine-tuned models, then our instantaneous optimization come into use. Our instantaneous optimizations are multifold. We have the adaptive tiling and auto-configuration, means that we are going to find the tiling and the memory-related parameters instantaneously. We have the universal operator fusion. It means that based on certain laws, we can automatically and universally fuse the operators to reduce the input and outputs. And also, we have the memory layout transformation optimization, which is a just accepted research paper. And this one is specifically optimized for transformers. And also, our techniques can also be adopted for the on-device training, which, to be honest, requires a lot of memory space, which is difficult for the current local devices, but we managed to deal with this through our optimizations. So for more generality, actually we have the optimization for the mobile DSP, for the mobile NPU, and also the other types of AI chips. We have the specific optimizations for the very long vector registers, and also for the VLIW packs of the instructions, and so on and so forth. So from the benefits, we can see that in the cloud computing, we can significantly cut the cost. And then for the previously very difficult of the edge computing, and we can enable the edge training, and also accelerated edge inference for all types of models. We use some of the examples, and this Stable Diffusion and its variance is actually an example. Actually, when we are working on this, Stable Diffusion is quite slow on the NVIDIA. It takes several seconds. It takes over 1 minute on iPhone. Currently, it's still about this speed. And it's not supported in Android. And it has over 1 gigabyte of the overall size. So our work of the OminiX starts from the Stable Diffusion. Actually, we extracted the operators for the different parts of the Stable Diffusion models. We can see that those are the different parts, and those are the different operators we have extracted, and those includes all types of Stable Diffusions from 1.4 to SDXL. And also, we have included operators of the diffusion transformers, which is a key of Sora, and also the different LoRa's, and also for fine-tuning. So we will generalize to the large language models, and we will derive the overall common set. So here is actually the memory use we have configured for the training and also for the evaluations. So actually, based on the different operator sets, we are going to combine the operator set. And then we are going to develop the OminiX framework. We are going to relieve the 2 gigabytes model size limitation of OminiX. And we try to build an open source framework, an operator set, dedicated for the large scale models. Because this 2 gigabytes model size limitation is not compatible with future large models. It's already not compatible now. So we start from a comparable models of the Snap Fusion. And then we are going to train a new model for the Stable Diffusion, but we can be compatible with existing models as well. And then for the compiler, or for this kind of runtime, we are developing the backend for the Android devices, iPhone and Mac devices, Intel devices, AMD devices, and so on and so forth. For the public release and open source, we're going to release a common operator set and the OminiX framework. We are going to release an optimized Stable Diffusion model, but of course, we are going to support other models as well. And then we are going to release the code generation support for the common operator set and Android, and also the Mac or iPhone edge devices. And our open source is going to be integrated with Rust and also the API and also the other front ends. So currently, we can see that on NVIDIA, we can accelerate Stable Diffusion to less than 0.4 seconds. On iPhone, we can make it 2 seconds, 3 seconds. On the Android, we can make it on the 6 seconds, and previously it is not supported, while we maintain the same quality. We can run a Stable Diffusion demo. We can see that this is purely on an iPhone. And then we can see that we already changed it to an airplane mode. This is already on an airplane mode. And then we can see that this kind of generation can be done on iPhone. And then we can see that we change a prompt. This is not even the best iPhone. Using the iPhone 15, it can even be faster. We can see that it takes about 5 seconds, and then the quality is the same as the original Stable Diffusion. So generally, Stable Diffusion is good for generating this kind of fictions and also generating the different scenes. For generating animals is not that good, but this is a problem of the general Stable Diffusion. So for the large one, the Stable Diffusion XL Turbo, we can see that how it actually works for the Mac devices. And then we can see that after we input a prompt, so this is done on a Mac. There is no connection of the servers, just on the device itself. And then we can see that after we click this, we start running. And then we can see that it starts running using this speed. And then in about less than 10 minutes, 10 seconds, and then it can generate 4 figures. So on average, about 2 seconds to generate 1 figure. So this is some of the demonstration here. So we can see that for the Stable Diffusion, previously in the cloud, for the OpenAI, DALL-E, and all, I mean, it's generally the cost is about 2 cents per image. But this cannot support the user's fine-tuned models. It has a lot of restrictions. But ours is the cost is 0 on the device, or very small on the actual cloud. And then we can see some other examples. We are going to run a Llama 2 7B. This is a large language model. And this is on an Apple M1 device. And this is also not using the GPUs, just on a Mac. And then we can see the speed here. And we can see that we are going to load this model. And this model is compatible with the GGML, which is the Llama CPP. And then we can give a description. We can see that this is actually the local writing. And then this is asking this to run 100 words of a story. The general speed at this moment is something like 70 tokens to 80 tokens for a weak, relatively weak M1 device, which is 3 years ago. For the currently M2 or M3, at most it can be accelerated to 110 and 120. But we are not fully optimized yet. So my guess is that this can be further accelerated by 50%. This is our guess, and maybe it is even conservative. So the speed in our understanding is totally comparable, or even faster compared with the current speed on an NVIDIA, because NVIDIA is also lack of optimizations. And also they need to use a very difficult to use compilation technique. And then I don't know whether the voice is okay, but then we can set the voice to see our overall integration of a chatting avatar. And this is real time.
When asked about whether you believe the reality is simulation, you say your brain says yes, but your heart says no. How could you elaborate on that?
Oh man, it's a fascinating topic, really. So, you know, when you think about the universe and the advancements in technology, it's interesting to consider the probability. My brain leans towards yes, because as technology evolves, creating a simulated reality becomes more plausible. Think about video games today compared to 30 years ago. They're incredibly realistic now. So imagine a future where simulations are indistinguishable from reality. Wouldn't it be possible that we're already in one? But then there's the hard aspect, right? That's more about our human experience, our emotions, our connection to this world. It feels real, and that's vital. It's like balancing the scientific perspective with our human experience. So what happens? It's a blend of possibility and skepticism.
Okay. Overall integration. And then this overall integration is using our framework of acceleration. And then this integrates everything, including the large language models from the text to speech, and also the speech to text, and also the animation. So everything can be done just using one GPU. So this can significantly reduce the cost. And this is not even a strong GPU. This is 3090 GPU, which is not even a strong GPU. And then we can make it real time. And currently, so we are going to open an API, and then if you're interested, you can test on our digital avatar, the talkative avatars. Okay. So our final thing is actually we are going to train and fully open source a 7B large language model. So from our training of a large language model for chatting, actually we have the experience of actually train from scratch a large language model. And actually, our objective is to make a fully open source model. And by saying that this is complete open source, it means that this is not only the model structure, but also we are going to open source the whole training script, all the training data, and also the training framework from scratch. So this is to overcome some of the community license limitation of the Llama or Llama 2 because they have some restrictions to use by the large companies. And also by completing this kind of whole open source of the model, we can broadcast the training process to community, and we can build a community, and the community can give feedback. And then they can see how the model is improved based on the community's feedback. And eventually, when we build an ecosystem together, and then this can eventually outperform and hopefully becomes the leading model of the open source. And also, by open source everything, we have some of the advantages. For example, we can handle the long context window like 100K. Currently, there is no such open source model supporting this kind of long context window. And also, if we are opening this kind of training data, we can perform better quantization and sparsity pruning. And then the model size can be reduced by 5 to 6 times. And this can better facilitate the edge deployment. Currently, because the Llama doesn't give any of the training data or the training script, so we cannot perform the quantization very well. So the quantization is very much lossy, and the pruning is impossible. So the edge deployment is having a big limitations because many of the edge devices is memory intensive. So there is a restriction here. There will be novelties in the architecture. For example, like the advanced architectures. And then we are going to incorporate the recent advances to support the large language model, to support the long context window, for example, like 100K, and also the mix of experts. And then our generated model can support the quantization-aware training, quantization, pruning, and this can further increase the speed anyway. So we have extracted the training data required. So now we have the high quality data. We have the coding data. We got the support from the star coder team. We have the math data, and we have the Chinese and the large language, which is weak in Llama 2 and also in Mistral. There are only less than 5% of the data in the training of Llama 2 or Mistral, which is a foreign language. So we have collected over 20 T data now. So if we consider the Chinese data, then the total data we may be possible is 30 T. This is 15, 20 times, 10 to 15 times more compared with Llama 2, and already more compared with Llama 3. And the training data and also the data portfolio will be released to public. So we'll have advantages in the metrics. For example, the general comparison of the evaluation metrics, and especially some of the evaluation on coding math and also the other languages. And also, the storage size can be reduced by 5-6 times without any metrics degradation. And this is comparison with llamas. So there are many of the advantages to facilitate the edge deployment, to facilitate the user deployment, and also the user's fine-tuning. We want to make this kind of community almost as prosperous for the user's data, for privacy conserving, for integrating with Rust, similar to Stable Diffusion's community, like CiviTime. So thank you very much. Thank you.